Hello boys and girls, welcome to part 3 of our solar powered cell phone charger series. If you've been following along, you know we've been playing with the MC33063 switching voltage regulator and trying to get it to do different things, and we've had varying degrees of success. Today we're going to look at the final part of the circuit. We're going to look at a technology or topology known as SEPIC, single-ended primary inductor converter. It was patented for many years. Somehow they let the patent lapse, and so this came into the market. Unfortunately, there's a lot of contradicting information out there, and today we're going to look at SEPIC and can we make it work with our MC33063 to do what we want, and can we explain it sufficiently. The important thing with SEPIC, it will give you a constant voltage output regardless of the inputs. The input can be high, it can be the same, it can be below the output voltage. The SEPIC will try and give you a constant voltage output, and that's very important for us. There I'm drinking today Jack Black's Cape Pale Ale. It's the first time I've seen this. It's a 4.4% alcohol, 35 IBU beer, apparently. Hoppy, cold classic and outright thirst quencher. Our dry hop CPA's got loads of citrus, pine, tropical aromas. Smashing it and getting in colder. We'll find that out as we go along. So let's get to the bench. Let's talk about SEPIC. Let's build the circuit and let's see if we can make our chip do what we need to. So the key to understanding these converters, we've looked at inductors and we know an inductor resists a change of direction in current, so it's a storage device, because what it does as the current increases, the flux around the inductor builds up, and as the current tries to change direction, the flux now will collapse and keep the direction in the same flow. So simply put, if we had our inductor, we're going to put a core there, and we had our switching device like that going to ground, and we then had a diode, a capacitor, again going to ground. We'd have something like that called a boost circuit. The problem here is that is our voltage, our supply voltage. There is no isolation to our output. If we short that, well, the current flows straight through. So SEPIC's first benefit of anything was really to say, let's put an isolation capacitor in there. Now we know a capacitor doesn't allow DC current to flow through it. It blocks it. So in a way we now have isolation. Let's start like this. We'll have our inductor, we'll have our switch going to ground, we'll have our capacitor, we'll have our rectification diode, storage capacitor. What happens if we put another inductor here? V out, VCC. Well, effectively what we've done is we've isolated the two circuits. So if I create a short here, because ultimately this will be back to DC over here, it won't really affect there. So now we have isolation. The second important thing is, if that's plus, that'll be plus. Our output voltage is not inverted. It's a very nice benefit of SEPIC. So if I have a positive voltage in, I have a positive voltage out. The third advantage of this combination, because what we're using is a boost circuit. If you remember, if our part 1 or part 2 of our video series, we talked about the boost series. We close that switch, the current will build up, so will the flux, and so we can increase the voltage. So SEPIC has got quite a few advantages. Disadvantages, we now need 2 coils. So my thinking was, can we make, or can we force the MC33063 chip to do this? Remember, my whole goal is to build this with things that I have on my bench, and not go out and buy separate components to do this. It's not the most efficient way of doing it. It's not the best way of doing it. I am trying to make the things that I have work. And that's important for students and people that want to learn electronics, is to learn to make what you have work. Not go out and buy the best solution. You don't really learn anything from that. Our beer, as we can see, nice and clear, nice head, nice citrus notes. Nice bitterness. So I've designed the circuit around this. Let's set the shot up, and we'll come back to our circuit that we've designed around the MC33063. So here's the circuit I've put together around our MC33063. Not very amazingly complex, not very difficult. We have a supply, in this case anything from 3 volts to we've actually designed for 14.7 volts. I have a little current sense resistor blocker there that will limit this chip. It will start switching off if it draws too much current. In other words, it will limit the switching on that circuit there, so we don't blow things up. So we have our supply, we have our current sense. Here we have a little Darlington pair. It's just a thing that transistor pair that allows us to switch higher currents using smaller powered transistors. We have a 100 microhenry inductor here. We have a 12 microfarad blocking, well, in our case, coupling capacitor, because remember, it will couple the AC, it will block the DC. So decoupling DC, coupling the AC. Another 100 microhenry inductor going to ground here. Schottky diode, a 1N5819. Bulk filter capacitor. A voltage feedback circuit. We're going to look at the data sheet. The comparator in here on VFB, voltage feedback, wants to see 1.25 volts. So by this division here, if I have 5.75 volts there, I will have 1.25 volts there. That comparator will be happy. Little LED with its just for indication. And here I'm actually not going to use a Schottky, I'm going to use a normal silicone based diode, because I want to drop that 0.7 volts. I want 5 volts, I do not want 5.7, 5.8, whatever, I want that. Down here, this takes a bit of time to explain. So the USB standards explain to us about whether a charger can deliver 250 milliamps, 500 milliamps, 1 amp, 1.5 amp, 2 amp, 2.5 amp, and so on and so forth. And they also explained to us that the device giving the power should be able to say, I'm a dedicated charging port, in other words a DCP, or not, or I'm actually something intelligent, in other words I've plugged my phone into my computer and it's exchanging data but charging at the same time. That's what this is about. This just happens to be the coding. In other words, I want to see 2 volts on D plus and 2 volts on D2 for Apple. And this is a bit of a pain in the ass because you don't want to go code it for Apple, for Sony, for whatever. So there are chips that do this. Remember, your phone will plug in here, and your phone has got a special chip that would say, hey, who are you? And it will talk on this D plus, D minus line, or 2 and 3 here, and say, who are you, what can you give me? This coding is what tells it I can do whatever. Now, there are dedicated chips that would give you that handshaking, and you can put them in the circuit. For me, I couldn't be bothered to buy the chip. It costs something like I don't know, from RS Components, $20, but then I must buy a minimum of 20 of them, so $400, and I have no use for it. So really, as a school project or something like that, no, it's not worth it for me. I'd rather just program it like this. Then we know we could plug our iPhone in and off we go. So what I'm going to do, I'm going to take this circuit, I'm going to breadboard it. We'll come back and look at the breadboard, and then we can discuss what we have there. Our beer, as it's warming up. Now I'm definitely getting now a bit of tropical fruit in the beer. It's nice and smooth to drink. I don't know about the 35 IBU, but no, that's neither here nor there. So let me breadboard the circuit. We'll come back to it and we can go through it, and I'll explain to you where we're going to probe and what we hope to see. Okay, before we look at the breadboard, I just want to mention that there is an application note from Texas Instruments, AN Alpha November 1484, designing a SEPIC converter. It's pretty much got all the formulas inside there that you need for calculating these different components, but this coupling capacitor, there is a lot of conflicting views out there. To make it simple and to understand how you're going to size that capacitor, because they don't actually tell you, what you need to understand is, in this inductor, the current is going to rise over time, it's going to deplete over time, and so it's going to go on. And ideally, you want to be in a thing called continuous conduction mode. In other words, that point there never reaches zero. So the current is going to vary between whatever you've calculated, 200 milliamps to an amp. So you'll have 800 milliamps of ripple current. That capacitor is sized to handle that ripple current. That's all you need to think about. There's no fancy magic naked virgins in Switzerland bearing chocolate, doing whatever. The capacitor is sized to carry the minimum of the ripple current. So if you understand that, you are 10 miles ahead of everybody else, because if that capacitor can handle that ripple current, well, if you do the maths, R equals V over I, the capacitor will definitely carry the ripple voltage. Remember, this is going to be a pulse doing this the whole time. To all intents and purposes, that square wave is AC. The capacitor will pass it. But if it can handle that ripple, is how well it's going to pass it. If it can't handle the ripple, well, you're going to lose efficiency. What will happen is if the capacitor is too small, the equivalent series resistance is too high, the capacitor will just die very quickly. You will end up with it either blowing up in your face, catching fire, or it will just fail and give up the ghost. So the thing that nobody's really explained to you, that capacitor is sized to handle the ripple current in that inductor. In this circuit, we've made that 100 microhenry, we've made that 100 microhenry. These capacitors are not coupled. In other words, it's not a single core with two windings around the same core. I don't have that sort of capacitor inductor at home. You could do that. You could have a single ferrite core, toroidal core, and you have equal turns around the same side, equal inductance. You could halve the inductance requirement there because your inductive coupling would cancel each other out, and that's one way of doing that. But the problem with that is higher powered circuits, you're not going to find off the shelf inductors that are wound like that. So using two separate inductors is not a problem. If they were commonly on the same core, well, then you've typically got a flyback converter, and you don't really need that for this circuit. The thing, because if you look at it, how is that voltage getting there? It's that capacitor that's coupling it. It's letting the AC component flow through to charge, and that's what's happening here, and that's the magic of the circuit. If you have to understand the DC side is blocked, it's the AC side, and because we've created a pulse over here doing that is AC. Okay, and that is what our capacitor is letting through. The problem with this chip, and that's what makes it so difficult, it doesn't have a fixed pulse width modulation. In other words, I can't say every 100 kilohertz this would happen. This chip is a busted. It does pulse frequency modulation as well. So it says, oh, I don't need so much load, so let's make 1 hertz. And we'll wait 49 periods, and then we'll switch on 1 hertz. Oh, but hang on, the load's picking up now. Oh, now we'll make it 2 hertz, 3 hertz, 4, and so it will pick up that frequency, and then it will go into varying the on time versus the off time. So this chip is a busted to make it work with SEPIC, but we can con it, and that's what we've done in this circuit. So let's get the breadboard out and we'll show you the points of interest. Right, so the first thing we notice is this capacitor block down here. I have 3 6 microfarad capacitors coupled together in parallel. So if we look at our circuit, it's that. That's just to handle the ripple. I didn't have any capacitors that could handle that on its own, so that's what I've done there. If we zoom in a little bit, let's see what you can see here. Down here I've just got 2 capacitors, 2 little capacitors in series to effectively half the capacitance for my timing capacitor. In here I have our MC33063 IC. You can't see nicely with all these wires, but that's our little MC33063 IC. There's our first inductor on the primary side, our secondary inductor over there on the isolation side. that over there is our little rectification diode, our output filter capacitor, our input filter capacitor. Nothing fancy down here. We just have our blocking diode. That's still a 1N5819. I'm going to change that to 1N4007. And what we'll do is, down here we will come and put in that circuit a bit later on once we happy with everything. So not really much to the circuit. Well, what we're going to do is we're going to probe a few points. We're going to probe over there. We want to, well, over here we want to see how good is our voltage regulation. We're going to probe over here. We want to see our, basically our switching frequency. And where else would we like to probe? So we got our output, we got our switching frequency. I don't know. Maybe we should probe on that end of the capacitor. Yeah, why not? So let's probe here. We'll probe with our yellow. Here we'll probe with our blue, channel 2. So channel 1 yellow, channel 2, and channel 3 magenta. And we'll see what's happening in this circuit. First we'll have a look at it with our bench power supply and see how it handles it. And then what we'll actually do is I'll solder some leads onto these solar panels. We'll put them in parallel. And we'll see if this thing can actually charge a cell phone. Right, let me get the bench equipment hooked up and then we can come back to that. Right, here's our breadboard hooked up. A yellow channel down here, our output, 0.1, point 2 is over there, our inductor, and 0.3 on the other side of our switching capacitor, our other inductor up here. So 0.2 down in there, 0.3 up here. And that's important because I want to show you that the inductors follow each other. Power supply, used to. It's off. I'm going to dial the voltage up here in increments. We'll have a look at the waveform here and have a look at what we're reading. The only thing I'm going to set is on our output channel. We'd like to see the RMS voltage output, currently 0. So I'm going to switch our circuit on at 3 volts. Can you see that? Let's just zoom in a little bit. We've already got our 5 volt step up. Unbelievable, eh? So we are, to all intents and purposes, we are boosting the circuit. We'll go to 4 volts, 5.3 to 5 volts, 5.4. So basically from 3 volts we are already regulating. I'm going to step it straight up to 15 volts. And what you can see is our output voltage is pretty well regulated. So I'm sitting at 15 volts on this side of the power supply that I'm supplying into the circuit. Remember, we're not driving any load yet, we're only driving the LED at 15 volts. We're pulling 18 milliamps, and let's just do a little efficiency calculation. So on our output, basically the only load that we have is this 180 ohm resistor. So we have what, 5.7 divided by 180 ohms is 31 milliamps. We can square that times 180. So we have got 180.5 milliwatts of power that we're drawing. On our input side we're putting in 270, so we divide that by 270 times 100, 66.852% efficiency. Let's go all the way down to 3 volts and we'll see what we get there. So we've got what, 5.5 roughly, 5.5 divided by 180 squared times 180. It's 168 milliwatts. Our power supply tells us 296 milliwatts of input power, so we divide it by 296 minus 3. Times 100. So that gives us 56.77% efficiency. Interesting. I'm not lying to you, we are putting in 3 volts, we're pulling 99 milliamps, there's our power, but that 3 volts that we're putting in our input, we can see we are getting 5.4 volt regulated on the output. So our boost circuit is working, our buck circuit is working. Let's step it up volt by volt. So now we've gone to 4 volt. What we're looking at, let's just zoom out a little bit. You can see our output power at the top. We can see our primary inductor, the first inductor, but what is important is you can see the second or secondary inductor follows the exact same profile as the primary inductor. So our capacitor, our coupling capacitor, there we go, over there is doing its job. It's letting everything go through, which is exactly what we expected, and that is how the magic of the circuit works. We go 5 volts, 6 volts, 7 volts, 8 volts, 9 volts, 10 volts, 11 volts, 12 volts, 13 volts, 14 volts, 15 volts. Let's just switch the amplitude down there, and we'll switch the amplitude down there. You can see it follows each other. Not bad regulation. 15 volts, we're sitting at 5.7 volts. So the circuit is regulating exactly like we want. The SEPIC is working exactly like we want. Below the voltage, if our input voltage is low, it's boosting it up to our required output voltage. Above the required output voltage, it's bucking it down to our required voltage of 5.75, which is exactly what we wanted. Remember I told you the 3K6 resistor voltage divider circuit. In other words, that 3K6 with that 1K will give us 1.25 volts here, and that's what it wants to see, and our comparator inside there is working. So even though I bought these chips off eBay and they might be fake and to all intents purposes rubbish, it seems as if our chip can be fooled into working as a SEPIC. So enough of this messing around now. I think what we should do, let me build that little circuit into the breadboard, wire up this USB, get our solar panels soldered in, and let's have a look at it, if it will charge the cell phone. Let me set that up. Right, and there are two solar panels wired in parallel. And there's the end of it. If we look at our breadboard, you can see I've taken the power off. Our positive and negative will go there. Our USB connector is wired in with its division resistors. So cell phone plugged in. And for those of you that think I do work alone and unsupervised, of course our chief QC engineer Rudy is having a look after Dad to make sure that I don't make cuck. So what I'm going to do, I'm just going to put these two panels outside. I'll connect these two wires up and we'll see what the circuit does. Let's set it up and I'll set the film up for there. Right, we have our solar cell connected. Let's just have a look at our scope. Let's go up and up and up and up and up and up and up. And what we can see is our scope is giving us, our output is 5.25 volts. So let's come down to our cell phone. We haven't plugged it in. This is our solar powered, or our solar cells that are now powering the circuit. You can see the cable runs off outside to my solar cells. So I'm going to plug the cell phone in. Oh well, nothing blew up. What we can actually see, did you see that? Our battery light has come on and it's actually charging it. There we go. So unbelievable. Let's unplug it again. If I plug it in, there it goes. So we have built a solar powered cell phone charger. Our two cells in parallel, which is what we set out to do. And yeah, that doesn't look too bad. Yeah, that really doesn't look too bad. Our output is 3.5, 3.6 volt RMS. I expect that to stabilize with time. Let me just set the trigger. So I do expect that to stabilize with time. Interesting, our primary inductor, our secondary inductor follows the primary inductor, and we're getting exactly what we want. So what I'm going to do is I'm going to let it charge for a little while. We'll see if it can actually bring this thing up to power. We'll come back and have a look at it then. And just in case you are doubting, if I press that, you see the battery light comes on. So it is doing its best to charge. So I'm going to let it run for a little while. We'll come back and we'll see, can this thing actually bring it up. Right, so it's been charging a little bit. Interesting enough, the only thing I want to bring your attention to is our output voltage to the battery. RMS voltage 4.11 volts. It's coming up. If you remember, it was 3 point something, 3.2, 3.6, somewhere around there. Slowly but surely I'm just watching this, and the the voltage is rising. I'm not going to record this. It just means that the current draw from the battery side, from the phone, is becoming less and less and less and less and less, and we actually are charging our cell phone. So I'm going to wait till we get to the boot, and then we'll see if we can catch it on film. But I think all in all, we've pretty much created a solar power battery charger, or cell phone charger. Interestingly, our output, you can see all these spikes and ripples and things going on. Yes, we could make that smoother if we put in a bit of a filter, a little bit of an inductor, capacitor, LC filter. We could smooth that out. I don't think it's actually important. If it hasn't broke the apple, it doesn't seem to be that important. So yeah, I'm going to let it carry on. 4.14 volts as we speak. So I'm going to let it carry on and charge, and we'll come back for the boot screen if we're lucky enough to catch it. Just while we're at it and we're waiting for our voltage to come up, you can see it's come up to 4.21. I've just put the oscilloscope's frequency counter on channel 2, in other words our primary inductor. I want you to note that it's 102.5 kilohertz. Excuse me. We've set the chip with the timing capacitor to run flat out. In other words, the minimum frequency that I wanted to run it is 100 kilohertz. What you'll notice is, as that voltage comes up and the current draw becomes less, that frequency will come down, and that's the issue that we have with the MC33063 IC. We're trying to con it, we're trying to bullshit our way around it, and this is the issue. We're trying to make it run really at its maximum frequency, so we always have a fixed pulse width modulation, in other words a fixed duty cycle if we can. Either the way what we've been speaking, 4.21 up to 4.22, 4.23, I'm going to let it keep running, and hopefully we will catch the boot of the phone, and we'll see where that crossover happens. And as true as Bob, I missed it. There you go. There's some card installed. Let's see if we can zoom in a little bit up there. Well, our cell phone is charging, so our cell phone, solar powered cell phone charger works. Just to note, there is no power coming in here. It's coming from our solar cell. Our bench power supply is off. Interesting to see on the scope. Our frequency is coming down as our voltage is coming up. So, have we built our solar powered battery charger? Yes. Or solar powered cell phone charger? Yes. The thing to note with the MC33063 is that it is a variable frequency chip, so you have to, if you're going to try and make it a SEPIC, you have to try and force it to run flat out, and then try and deal with it there. We could make it higher powered. We could put a MOSFET or something in the switching circuit so that we could switch a higher current MOSFET transistor by junction transistor. It's your choice. Obviously you're going to do the maths, and you're going to have to work out the losses and what is is best for you. So I'm going to consider this circuit successful. We've got our solar powered our solar panels that are charging our phone. That's what we set out to do initially. It all began with an intern that came to me and said, how do we build this? And I said, oh, just put a regulator in between. Then I got to thinking, and then I got to thinking what I had on my bench, and could we use it efficiently, or as efficiently as we could use it. So I'm going to consider, or I'm going to declare this project as closed, and I'm going to declare it as a success. So we'll wrap up, we'll get on the closing shot, and we'll take it from there. So boys and girls, we set out to build a solar powered cell phone charger. I think we've done that. We've proved that if we use a SEPIC converter with this chip, we can make it work. I think it was successful. As always, I hope you learned something. I hope you had fun. I had fun. Always have fun. Our beer, our Jack Black, Cape Pale Ale. It's a relatively nice beer. It wouldn't be my go-to beer. It's just me. I'd give it a drinkability of about a 3.5 out of 5. Perfect. But for myself and Rude, we hope you enjoyed this. As always, take care. Be safe. We'll catch you next time. Cheers.